record on the computer. There we go. Very good. So welcome everybody to another Shocklab seminar. We're really happy to have Jacobi here today, who did her master's at Stellenbosch and is now working in the real world. Oh, wonderful. Thank you very much. You've just put a link in there. Now working in the real world at Capitec, also working in machine learning. So yeah, we're super happy to hear about your master's work on inference.
Okay. Just going to share my screen. Just let me know if you can see that.
Yep, perfect.
Okay. Okay, yeah, so my talk is basically slides from this notebook. So I put it in the chat. If at any point you want to reflect back on it, then you're welcome to do that. I've quite a bit to get through. So yeah, if I lose you at some point, then that's also, you can refer back. So today's discussion is an introduction to variational Bayesian inference, and then we'll look at one of its applications in deep learning, which will be the variational autoencoder. But before I get to variational inference, I'm just going to do a brief background on Bayesian inference, just to make sure we're all hopefully on the same page before introducing variational inference. Okay, so Bayesian inference. So assume we have some observed data, x1 to xn, and we assume that it was generated from some probabilistic model. Let it be P with unknown parameters theta. Now, a typical task that we want to solve is to infer suitable values for theta given these observations. So most of you should be familiar with maximum likelihood estimation. So that's where we estimate the parameters of our assumed probability distribution given these observations by maximizing the likelihood function. And this is known as a frequentist approach because it provides us with a single point estimate of the parameters. Now, Bayesian approach is slightly different in that it applies Bayes' theorem and provides us with a complete probability distribution over our parameters. So instead of just treating our parameters as fixed but unknown values, we treat it as a random variable, and then we infer a probability distribution over these variables given our observations. So just a quick look at Bayes' theorem, which states that the conditional probability distribution of our parameters theta given our observations is equal to the likelihood of our observations given the parameters times the prior probability of just the parameters divided by the marginal likelihood of our observations. So if you just look at the terms in a bit more detail, the prior distribution expresses our prior knowledge about theta before we observe any data. Then the likelihood, that is the likelihood of our observations given our current belief about theta. Then the posterior, which is what we aim to obtain in Bayesian inference, that is the updated probability distribution of theta after these observations are considered. So you can see how Bayes' theorem corresponds to a form of learning where you have some prior knowledge or prior beliefs, and then given data, you update your beliefs to get an updated view of your parameters. Okay, and then the last term is the marginal likelihood or evidence. And this is the probability of our observations, irrespective of theta. And we obtain that by marginalizing out theta. So you integrate over the joint distribution. And obviously we're assuming here that theta is continuous. If theta was discrete variables, then we would take the sum over all possible values of theta. And it's this marginal distribution that causes problems with Bayesian inference. Because of this integral, it can easily become an intractable problem to solve. And if we cannot solve the marginal, then we cannot find a closed form solution for our posterior distribution. And that's where variational inference will come in, but we will get to that at a bit of a later stage. Okay, and also just shout if you have any questions, and I must stop, otherwise I'm just gonna carry on. Okay, so let's quickly look at this at the end of an example. So we assume we have some observations given in this figure, and we assume that they were generated from a multivariate normal distribution where we know the covariance matrix, but the mean vector is unknown. And we want to infer a suitable value for this mean vector given our observations. So basically just our likelihood of observations, and we assume that's normally distributed where we know the covariance matrix. We say it's identity matrix just to keep things simple. Okay, so if you look back at Bayes' theorem, we now have this likelihood term, but we need to choose a prior distribution over our parameters. But we also said that this marginal typically makes Bayesian inference a difficult problem to solve because of this integral. But if we wisely choose our prior, then we can make this a simpler task for ourselves. And to do that, we can make use of a conjugate prior. So a prior is called a conjugate prior for the likelihood function if both the prior and posterior distributions are in the same probability distribution family. So this prior is conjugate to our likelihood if both the prior and the posterior are in the same probability distribution family. And so we know that a multivariate normal distribution is a conjugate prior for the multivariate normal likelihood function with a known covariance. And therefore, a good choice for our prior over our unknown mean is to choose a normal distribution. And then we know that the posterior will also be normally distributed. Okay, so since we have now a conjugate prior for our likelihood, we know that the posterior distribution of our unknown parameter mu will also be normally distributed. And it is a known result that the hyperparameters of this distribution are given by these terms. So you can go and do the derivation. I think even Wikipedia shows how to do that. But you see how the mean of the posterior distribution of our unknown parameter mu is a weighted sum of our observations. Okay, this is just a function to calculate those hyperparameters of the posterior distribution, and then we will plot it. And this is just to illustrate the difference between a Bayesian inference approach and a frequentist approach like maximum likelihood estimation. So the blue dots, those are observations. Currently, we assume we only have 2 observations. The green cross, that is the true mean that we are trying to estimate or infer. Obviously, you wouldn't know that generally, but this is just to illustrate. Then the purple cross, that is the maximum likelihood estimate of our unknown parameter mu. And if you have worked with maximum likelihood estimation at all, you will know that for a Gaussian distribution, the maximum likelihood estimate of the mean is just the average of your observations. And so we see this purple cross lies exactly between our 2 observations. But it doesn't give us a sense of how certain we actually are about that estimate. We only have 2 observations, so we obviously can't be very certain about it. And this is where there's a difference with a Bayesian inference approach. The red here represents the posterior distribution over our parameter mu that we obtained using Bayes' theorem. And it's a Gaussian, so it has a mean, the red cross, and it has a covariance matrix associated with it. So these circles represent the first, second, and third standard deviation from this mean in the x and y direction. And we see that the true mean lies within 2 standard deviations of our estimated mean.
Sorry,
but as we,
can I just ask a quick question here? So you haven't plotted the prior here. So presumably
no.
the prior would be sort of somewhere to the left of...
Yes.
Yeah.
So we chose our prior to be with mean 0, an identity matrix.
Perfect.
So that's a good observation. So the prior would lie around here.
Yeah.
And that is why the mean here is skewed to the left. Because we have very little observations, our prior is still dominating in a sense. But as we get more observations, we want our estimate to be based on those observations more than our prior. And obviously you can change the prior based on how much prior knowledge you actually have. In our case, this is a kind of uninformative prior. It doesn't tell us much because we don't know much. And so we will rely more on our observations to inform the shape of the posterior distribution. As you see, as you increase your number of observations, how the posterior distribution kind of zones in on the true mean that we are trying to estimate. Okay, so with a Bayesian approach, it allows us to introduce prior knowledge about our unknown parameters. And it also allows us to incorporate uncertainty in the parameter estimates to take into account that we only have access to limited data. Okay, so then just another example to introduce a concept of a latent variable model, which will be important for the variational autoencoder. So in the previous example, we had parameters that were unknown. And these parameters were global to our model in that they affect all of our observations. Now, in a latent variable model, you have latent variables, which are typically denoted by Z, and we assume that each observation is associated, in our case, with a lower dimensional latent variable Z, which is not directly observed. And for our example, we are going to assume that each observation X can be decoded from Z using a noisy affine transformation. So the likelihood of your observations is a normal distribution where the mean is given by this affine transformation of the latent variable Z, where Z itself has a normal probability distribution associated with it. Okay, and we will specifically be looking at the MNIST dataset, which consists of images of handwritten digits. So the dimension of our observed space is 784, and we are going to choose our latent dimension to be of size or dimension 2. And this is just to easily visualize our latent space. Okay, so just some examples. I'm sure you have come across the MNIST dataset before. So now we have a number of unknowns in our model. We have the parameters mu, sigma square, and w, and then we have the latent variables Z. So you can use maximum likelihood estimation to get just fixed estimates for w, mu, and sigma square. And you can go look at the notebook to see how we obtain those values. You have to marginalize out your latent variable Z. And then you can, based on that, derive maximum likelihood estimates. But just for the sake of time, I'm not going to go through that. Instead, I'm going to look at the Bayesian inference approach to infer a posterior distribution of a latent variable Z, which is relatively simple because this is a simple model. So the prior is again a normal distribution, and we know that it is conjugate to itself. So both the likelihood and the prior are normal. So we know that our posterior distribution will also be normally distributed. And so you can go look again at the notebook in the appendix. There is a derivation. It's not too difficult to show then that the parameters of the posterior distribution of our latent variable Z given observations is a normal distribution with these hyperparameters. Okay, and then we can just visualize or see how that looks. So you can take an observation and encode it. And with encoding, I mean we just calculate this mean of the posterior distribution. And we plot it. And it's two-dimensional, so we can easily visualize that. And we see that how different digits are encoded to certain regions in the latent space. Like 9 and 7, they are encoded to the same region, and they look pretty similar, so that makes sense. Similarly for other digits. This is not great, but yeah, we can see something is happening. Okay, so that is encoding it, but it's also interesting to note how different regions in this latent space then decode to different digits, and how there's a smooth transition between the different images that you generate. So with decoding, you sample from your latent space, and we will sample in a grid and decode it by applying this affine transformation. So basically, we're plotting the mean of the normal distribution associated with your observation. And in this sense, we can generate new digits or new images of digits. They're not great, but we can see that some were captured well, like a 0 and a 9 and 1. And this looks something like a 3. But we can definitely improve upon that, and we will get to that with the variational autoencoder. Okay, so that was just a quick look at Bayesian inference, and now we're getting to variational inference. So in the previous two examples, we made use of conjugacy to ensure that the posterior distribution was actually easy to derive and to compute. But like I said, it's not always possible, and for most real-world scenarios, the posterior will be intractable to compute. And with intractability, that can either mean that you cannot derive a closed-form solution for that integral, and even if you were to use numerical integration, it would not scale to very high-dimensional problems. So computationally, it would be intractable to perform Bayesian inference. So in these situations, we can make use of approximate inference techniques. And there are a number of them out there. Here I just mentioned a few. One of the earliest ones was Laplace approximation, which basically approximates your posterior with a Gaussian or normal distribution. Then you have your famous Markov chain Monte Carlo methods, where you construct a chain of samples that has your target distribution as the stationary distribution. But those can be computationally quite expensive and slow to do. Then another one is expectation propagation, which is very similar to variational inference in that they use the same measure of distance between your approximation and your true posterior, but in a different way. But I'm not going to go into that in details. Instead, we're going to look at variational inference. Okay, so whereas methods like MCMC takes a sampling approach, variational inference views the inference task as an optimization problem. Okay, so what exactly does that mean? Well, first, let's just look at our problem again. We want to apply Bayes' rule to get the posterior distribution of our latent variables, but we cannot solve this exactly. So instead, what we do is we find another easy to compute distribution Q, such that this proposal distribution is as close as possible to the true posterior. So we do that by first proposing a family of approximate or proposal distributions over our latent or unknown variables. And this family is parameterized by 3 variational parameters, which are typically referred to as a phi. We then find the member of that family Q, which just corresponds to finding the setting of the parameters phi, so that the approximation is as close as possible to the true posterior. And this closeness is measured in terms of the Kullback-Leibler divergence, which is typically just known as the KL divergence. Okay, so just quickly a look at the KL divergence. This is a quantity from information theory that measures the disparity between 2 probability distributions. So the KL divergence of a distribution P from a distribution Q is defined as the expected value of the logarithmic difference of these 2 distributions, where the expectation is taken with respect to the distribution Q. Okay, so the KL divergence is not symmetric, it's non-symmetric, and so it's not really a true distance metric, but it is non-negative, and it is equal to 0 only when your 2 distributions are exactly the same. Okay, so given a true but intractable to compute posterior and a family of proposal distributions, the variational inference objective is to minimize the KL divergence between your true posterior and your proposal or approximate distribution. So just to look at it visually, the blue circle, that is your family of proposal distributions. And the aim is to find a member of that family that is as close as possible to the true posterior. Now, we want to choose a family Q to be flexible enough so that this distance is as small as possible, but also simple enough so that it still remains efficient to optimize this problem. But typically, Q would not actually contain your true posterior, so you would not be able to ever find an exact solution, but you can get an approximation very close to the true posterior. Okay, but if you were paying attention, you would notice that the KL divergence actually contains the true posterior, which we were trying to approximate in the first place. So we cannot use this objective directly to solve this problem that we have. And this is where the elbow comes in, or the evidence lower bound. So if we look again at the KL divergence, this per definition, it is, Per definition, it is the expected value of the logarithmic difference of these two distributions. But we know that we can rewrite this posterior using Bayes' theorem as the division of the joint by the marginal. And since it's a log, that becomes the difference between the two, and you can take out this term outside of the expectation because the expectation is with respect to your distribution Q. And then all we do is to reshuffle these terms a bit. So we take the log marginal to the left and the KL divergence term to the right. And then we can notice two things. First is that this log marginal is a constant value with respect to our choice of approximate distribution. So during optimization, this value will remain constant. Also, the KL divergence is non-negative per definition. So on this side, we have a fixed value. On this side, we have something that is always positive. So by maximizing this term, which is known as the elbow, we will indirectly be minimizing the KL divergence term. And this elbow, well, it's called the elbow because it is the evidence lower bound. It will always be upper bounded by this constant log marginal value. So in variational inference, the goal is to minimize the KL divergence, but we achieve that by maximizing the evidence lower bound, or elbow. Okay, so now we can move to an example to see this in action. So let's consider the following model where we have observations X that are normally distributed and the latent variable Z that follows an exponential distribution with hyperparameter lambda equal to 1. Okay, this figure just shows how these density functions would look. Just note for exponential distribution, the density is 0 if Z is negative. Okay, so for given observation, we want to infer the posterior distribution of our latent variable Z given that observation. So first we apply Bayes' theorem. We're first going to try the standard approach of applying Bayes' theorem and try to solve the posterior distribution exactly. So first we just write out all of these terms. The likelihood is a normal distribution, so we know how that looks like. The prior is an exponential distribution. This is just the indicator function to represent that situation where the density is 0 if Z is negative. So the indicator function will evaluate to 1 if Z is greater or equal to 0 and 0 otherwise. And then the denominator, or the marginal distribution, that is the integral over the joint distribution for all values of Z, which is from 0 to infinity. Okay. Now, the integral in the denominator does not have a closed form solution. And this is a relatively simple example, so we can actually apply numerical integration to solve this problem. But this approach does not scale to higher dimensions, and inference therefore still remains intractable in practice. So instead, we're going to consider using variational inference to solve this problem. But first, we are going to apply numerical integration to get an idea of the true posterior, and then we will compare our approximation to that true posterior. Okay, so just some functions to implement these, the exponential and normal density functions, and also the true posterior using numerical integration. Okay, this is just to generate the plots. Okay, so here we see the blue, that is our prior density. The red is the joint, and the green is the true posterior. And we plot these for different fixed values of our single observation. So in this example, we only have one observation to keep things simple. Okay, so now we want to approximate the posterior using variational inference. Since we can't compute it exactly, we can propose a known and easy to compute distribution and optimize its parameters to obtain an approximation close to the true posterior. So we are going to propose the exponential distribution family as our family of proposal distributions with parameter phi. So we need to optimize phi to obtain an approximation close to the true posterior. Okay, but like I said, we can't use the scale divergence directly, so we maximize the elbow. And this is just some maths. We can take this expression, which is the elbow, just evaluate the expectation, and then you will get to this term here at the bottom. How do you obtain the optimal value of phi? Well, we can take the derivative of that expression with respect to phi, set it equal to 0, and then solve for phi, and you will find that in this case, we can easily derive our optimal setting of phi to minimize the scale divergence between the approximate and true posterior distributions. Okay, so this just will plot that approximation. Just note that phi we calculated using that expression we derived on the previous slide. And then our approximate posterior is again an exponential distribution where the parameter is given by phi. Okay, so in this plot, the red is joint, the green is the true posterior, which we obtained actually via numerical integration. And then the blue is our approximation to the true posterior. And we see for x, for smaller values of x, the approximation is relatively close to the true posterior. But actually, as we take larger values of x, the approximation is pretty far off from the true posterior. And this is the trade-off that you have with variational inference. Because we choose a simpler distribution to use as our posterior, we cannot always closely match the true posterior. Okay, so this was a simple problem with only a single latent variable, and we could easily derive the optimal value of the variational parameter by taking the derivative of the expectation. But yeah, usually you can't do these derivations by hand, or it would be really time consuming. And so a classical approach to performing variational inference when you have multiple latent variables is to make use of the mean field variational family as your proposal distribution. So in this family, you assume that all your latent variables are mutually independent, and each latent variable is governed by its own distribution or factor with its own variational parameters. And then you can use an algorithm known as coordinate ascent variational inference to iteratively optimize the variational parameters of each of these factors. So you will keep all the factors fixed except one, and you would optimize its variational parameters. And then you would move on to the next factor, and you would continue that process until convergence.
Sorry, can I
But
just
the story, yeah?
So can I just ask a couple of questions here? The
Yes.
first one is, so if you were looking at some data being generated and you're taking measurements as you go along, you'll calculate each time your approximate posterior, and essentially you then want to use that to update your prior, because now you have some more information. When you're doing this, would you use this as a sort of weighted new prior? Or would you simply replace the prior with your posterior?
I'm not sure. I guess you would replace it, but then it depends on what your original prior, the functional form of your original prior was versus what you use as the approximation. Yeah, I haven't seen anything like that, so I'm not too sure.
Okay. And then just a second question. So here you use the KL divergence as the measure between the distributions. So there are other measures that one can take between distributions. Does the KL divergence give you a particular sort of a better optimization, or what's the reason for using that particular divergence?
Interesting question. I haven't thought about that. That is the classical one to use.
Sure.
Yeah, sorry, I don't actually know.
No, okay.
Yeah, if others have been used. Yeah, I think I remember there was. It's still. I was thinking it was the Shannon, something to do with Jensen-Shannon divergence, which is quite similar, but it's kind of like a weighted KL divergence where you use the approximate and the true one.
Okay.
You weight them. So there have been other ways, yeah. But I can't recall the exact details.
Sure. Thank you.
Okay, cool. So yeah. Oh, I wanted to say, yeah, with these algorithms, they still typically require derivations because you have to derive the updates that you apply at each of those steps in your iterations. And so it can also be a tedious problem to solve. So an alternative to coordinate descent is to use gradient-based optimization because we have all these automatic differentiation libraries at our disposal. So it's a good way to scale variational inference to large problems and data sets. And this is the idea behind stochastic variational inference. Now, there are many papers on these topics, so we're not going to go into the details of these algorithms. And there are also many nuances between the different algorithms, slight differences in how they tackle the problem. But instead, we're just going to look at the main concept, and we will experiment performing stochastic variational inference using Pyro, which is a probabilistic programming language built on Python and the PyTorch deep learning framework. Okay, so we're going to look at the same example, the exact same example we had before for the IMNIS dataset. And this time we're going to solve it using Pyro, which requires very little effort from our side. So we will programmatically define the model, and then we can automatically construct a suitable variational family for this model via one of Pyro's AutoGuide classes. And then we can optimize the model and the variational parameters via Pyro's implementation of stochastic variational inference. And underneath this, this leverages automatic differentiation to estimate the gradient of the elbow and then apply those updates to optimize our parameters. Okay, so this is our model typed out, and then we can define it programmatically using some of Pyro's functions. So we our parameters was mu, sigma, square, and w, and we can define those using pyro.param function, and we can specify some constraints like sigma squared should be positive. And then we can also specify our variables. So Z is a normal distribution with mean 0 and the identity matrix as the covariance matrix. And X is also a normal distribution where the mean is given by this transformation of Z. And we use this argument to show that X is actually the only variables that are observed. And then it's easy to construct a proposal distribution that we will use in variational inference. In this case, we make use of the auto-diagonal normal. So this is a mean field proposal family where each of our unknown parameters, we assume that the unknown variables are mutually independent and that they are normally distributed. And then Pyro will optimize the variational parameters for us. Okay, so this is a standard training loop. We specify our optimization algorithm, just the variation of Adam, sorry. Our loss is the elbow. And we use this stochastic variational inference algorithm that Pyro provides to optimize the parameters of our model and the variational or the variational parameters of our approximate posterior. And then we just perform multiple steps of this optimization and until convergence, and we can just plot the elbow. So this is the negative elbow, minimizing the negative. It's the same as maximizing the positive. Okay. And so we have trained a model, and now we can extract the optimized parameters and the estimates of the latent variables. So yeah, we just extract the optimized parameters, and then we will use the median of the posterior distribution as an estimate for our latent variables given the observations. And we use that so that we can generate this same plot that we had before. So these are the median of the latent variable Z for each of the observations. And it's the same model, so it looks similar to what we had before, how different digits are encoded to certain regions in the latent space. And we can reverse that process. We can sample from this latent space and plot the generated images. And again, it looks similar. Some digits are represented nicely, but not all of them. But yeah, it's expected. We have a very low dimensional latent space, and we make use of only linear transformation. So this can only get better. And that leads us into the variational autoencoder. So in the previous example, we had this model with which we can decode samples from a lower dimensional latent distribution to obtain samples of high dimensional observed images. And we can also reverse that process and encode our images into a lower dimensional representation. And we made use of variational inference to obtain an approximation to the posterior. But to keep the model relatively simple, we assume that X can be decoded from Z using only that noisy affine transformation. But this is rather restrictive, and yeah, like I said, not all the, or as you saw, not all the digits were represented equally well by this model. So what if we replace this simple affine transformation with a more complex and general nonlinear transformation? And that, in a way, leads us to the variational autoencoder. So we can replace the linear transformation with a general nonlinear function f, where f is a neural network with weights and biases. And the parameters of this neural network are typically referred to by theta. But we do not only want to decode, we also want to encode our data points to the lower dimensional representation set. But deriving a closed form solution for the posterior is not necessarily easy or possible, especially if you're using more complex functions. So again, we can make use of variational inference to approximate this complex posterior distribution. And then similar to the model, we can use another neural network as the encoder in this proposal or approximate posterior, represented by G, where its weights and biases are given by the parameter phi. So our objective is to obtain good values for the weights of the neural networks F and G. And we do this by optimizing the variational inference objective, or the ALBO, by making use of stochastic gradient descent and automatic differentiation libraries such as PyTorch. So this corresponds to the stochastic variational inference, where we use batches of data and automatic differentiation to optimize our parameters with respect to this objective. But now the ALBO is given by an expected value. And in the first example, we could actually write out this expectation, which was easy to evaluate. But if this the joint and the approximate posterior is given or contains neural networks, then that becomes difficult. So instead, we estimate the ALBO using a Monte Carlo estimate. And the Monte Carlo estimate is obtained by taking many samples from your distribution and then evaluating this expression and taking the average of, or taking the sum over that for all of your samples and then averaging it. But for the standard VAE, we use only a single sample to estimate this expectation. There is follow-up variations of VAEs that use more samples to estimate the ALBO, but in the vanilla case, use a single estimate, and that does give good results. So this joint distribution over our observation and latent variables, that is known as the generative model or the decoder. And our approximate posterior is known as the inference or encoder model. And together these form the variational autoencoder. So just to show it visually, our objective is the ALBO. So we need to compute or calculate this for a given observation X. So a single pass through this model takes your observation X, it passes it through the encoder neural network, which outputs the parameters of your approximate posterior. The approximate posterior is then defined by these parameters, so we can sample from it and generate the sample Z. And we can also calculate the density of that sample Z under the approximate posterior, which is this term here in the ALBO at the bottom. We then pass that generated sample of Z to the generative model or decoder, where we pass it through the decoder neural network, and it outputs the parameters of our likelihood function of our observations. And then we can also calculate the likelihood of the sampled latent variable Z under the prior of the model, and we can calculate the likelihood of our original observation given this likelihood function. And together we use those to calculate the ALBO. And then from that point on, you can get the gradients and perform the optimization step. Okay, then another or final important part of the VAE is known as the reparameterization trick. So computing the ALBO required sampling from the approximate posterior. Here on the top left, we have to sample from the approximate posterior. But in order to optimize the objective with stochastic gradient descent, we need to compute the gradients of the objective with respect to those parameters phi. But if you were to directly sample Z from Q, then it's not that easy to backpropagate our gradients through that random variable Z. So what we instead do is to externalize the randomness of Z by reparameterizing it as a deterministic and differential function of phi x and a new random variable epsilon. And this allows us to backpropagate through Z. So this is known as the reparameterization trick. Just to show how that works. So instead of sampling Z directly from your approximate posterior distribution, you instead sample epsilon from just a standard normal distribution, and then you transform epsilon using the parameters that were the output of the encoder neural network to obtain your sample Z. And then based on this transformation, Z will still be normally distributed with this mean and variance. But you externalize the randomness to the variable epsilon. Okay, so that is the theory behind the VAE, and now we can implement it and train it on the MNIST dataset and then compare the results to the previous example. So yeah, we're going to use PyTorch's module class. And the complete VAE is a single model that can be trained end-to-end using that ALBA objective, but it consists of two main components, which was the encoder model and the decoder. We each of those has a main component, the neural networks G and F. Okay, I'm just quickly going to go through this, but it just shows how you can implement a VAE, which, like I said, consists of the encoder and decoder. A forward pass through the VAE passes your observation through the encoder, from which you can obtain a latent sample Z, and also the density of that sample under your approximate posterior distribution. You then take that latent sample and pass it through the decoder neural network in order to compute the joint density of your observation and your latent sample, and then together you use those to compute the ALBO. And then just a look at the encoder neural network. Maybe just quickly look at the reparameterization trick again. So you will pass your observation through the encoder neural network to get the parameters of your approximate posterior. And then you sample epsilon from a normal distribution and you transform that epsilon using these parameters to get your sample of the latent variable. Okay. And then your neural network, not much to see, basically just using convolutional neural networks since we are dealing with images. And then the decoder part of the VAE, which takes your latent sample Z and passes it through the decoder neural network. And it calculates the prior and the likelihood of your observations in order to get the joint likelihood of your observations and latent variables. And then just the decoder neural network, which is also makes use of convolutional steps. Okay, then just putting it all together to get a VAE model, and then we can train this model, which optimizes the parameters phi and theta simultaneously. So optimizing the parameters of your model and, in a sense, the variational parameters of your approximate posterior at the same time. So this is just a standard training loop, and then we can plot those latent encodings again. So we take observations, pass it through the encoder neural network, which outputs the mean of the posterior distribution of our latent variables, and we can plot that, and we see that there's much better separation of our digits in the latent space. It was still not able to distinguish between all of them, so 9 and 4, it seems, are still encoded to the same region in latent space, but definitely a lot better. And this is through using those more complex neural networks. And then we can also reverse that process to to generate new samples by sampling from the latent space and passing it through the decoder neural network. And as you can see, you get much better images of digits. So yes, that is it. Thanks. So with the VAE, what differentiates it from just a standard autoencoder is because you have that distribution in the latent space, it serves as a regularizing factor, and that allows you to actually sample from the latent space and generate new images that were not seen before.
Wonderful. Yeah. Thank you so much. That was incredibly clear. Really, really nice description of a lot of really important ideas that I think are often made sort of more obscured than they need to be. And I thought the sort of plots and things that you did there were actually some of the clearest representations I've seen of this anyway. So thank you very much for that. Great.
Yeah, it took a while to look through all the different ways of saying things to what is actually happening.
I bet. So I'm actually trying to write something at the moment on some of these things, and you've done a much better job than than I've been able to. You've actually clarified some things for me there. So thank you very much. Yeah, does anybody have any questions?
I have a comment. I think this notebook is actually a very nice complement to the deep learning in Daba practical on Bayesian inference. So if at some point you want to extend this, it might be a useful contribution in that sense, maybe for next year's in Daba or something like that, to because they sort of avoided the topic of variational inference for the most part.
Okay.
Yeah, I thought it might just be an interesting way to sort of tie it into other work.
Yep.
Okay, thanks.
Absolutely agree. Tim.
Hi. Yeah, that was a really great talk. I was just going to ask about the reparameterization trick. So I know that, I don't necessarily know all the theoretical details, but I know that's been shown that, that's something you can do when Z comes from a normal distribution. But I was going to ask, are there potentially issues when Z comes from some sort of more exotic distribution where we wouldn't be able to do this?
Yeah, so some of the work is incorporating normalizing flows. I don't know if you're familiar with those in your in the posterior. So then that in essence changes this transformation to a much more complex transformation, but it remains deterministic and differentiable. And that is basically the key. As long as that holds, then you will be able to still apply this trick.
Okay, great. Thanks.
Yeah, I also had actually that in the back of my mind, and yeah, that's also the clearest answer I've seen to that question. So thank you.
Okay.
Yeah, does anybody else have any questions? If not, let's thank Jacobi again. That was really fantastic. I may send you some questions at some point.
Yeah, please do.
Yeah, you may have just become the expert on this for us to turn to. But yeah, wonderful. Thank you so much for giving a presentation.
Thanks for having me.
Pleasure.
Yeah,
wonderful.
it was nice.
Thanks everybody. Cheers.
Bye.
Bye-bye.
Bye.